Hello, I'm Julian Stander and I'm a lecturer in mathematics and statistics at the University of Plymouth. And today I'm going to talk about modeling share prices using Brownian motion. And Brownian motion is a concept that you may not be particularly familiar with. You may have heard about it, but I will try to explain it. And Brownian motion is in fact based on the normal distribution. So what I've got here in my R graph is a plot of the price of Marks and Spencer's shares. So the price is here on the vertical axis against time, which I've displayed on the horizontal axis. And you can see from this plot that we basically have a price that wiggles around as time goes on. At a certain point, there's a sort of decline, there's a drop, and then more recently, there's quite a big dip in this share price, probably caused by the coronavirus pandemic. So when we do our modeling of this data later, we will probably only look at it up to the end of last year. Okay, so what we can see from that graph is that share price is a process that wiggles around, and what we need is some form of mathematical model to help us understand and to explain that wiggle. And that model is based on Brownian motion. So I'm now going to run my code and I'm going to show you, hopefully, a plot of Brownian motion. So here is a plot of Brownian motion. And we can see that this, again, just like the share price, wiggles round. So what I'm doing here is I'm plotting the value of Brownian motion against time. So what Brownian motion is, it's a mathematical model for a random process, sometimes called a stochastic process, and it's basically a wiggle. Now, Brownian motion, as I said before, is based on the normal distribution, and we'll see exactly how it's based on the normal distribution shortly. Brownian motion is named after a man called Robert Brown, who noticed the movement of tiny particles under the microscope. These particles were themselves wiggling round, and he reported this, and this was around 1820, and hence the name Brownian motion. Einstein worked on Brownian motion, and I think he wrote about it in 1905. And then it was put on a very firm mathematical footing by a mathematician called Wiener in 1923. Okay, so we've seen here a graph of Brownian motion, and we've denoted Brownian motion as B of t, where t is used to index time. Now, I could have written this as B t to indicate that Brownian motion is a function of time running on the axis here. But to save writing a lot of brackets, it's traditional in this topic to write B with a subscript, just like that. Okay, so there's one Brownian motion sample path that wiggles round, and I can show a second one, and that wiggles round in a different way. And I could go on and do that, and I could show a large number of these paths. And indeed, if my code performs, I will show in this plot here 200 Brownian motion sample paths. So let's just concentrate on the picture on the left. What I've got here is those 200 sample paths, and we can see they're spreading out. And I've put these lines here as an indication of how these paths are spreading out as time goes on. So I guess the idea of that in the modeling share prices context is that the further you look ahead, the less certain you are. But the message of that plot there is that these paths wiggle around but the amount of wiggle increases as time goes on. And what I've plotted in the right panel is the final values that I'm seeing there as these dashes and their theoretical distribution, which happens to be a standard normal distribution. So it's a feature of fact about Brownian motion that if I ask what is the value of Brownian motion at time 1, well, that's a random variable. It depends on the Brownian motion sample path up to time 1. But what we can say about it is that it's normally distributed with mean 0 and variance 1. And in general, Brownian motion at any time t, so whatever time t we choose, we can say, how are the values of Brownian motion distributed? They follow a normal distribution with mean 0 and variance t. So, as we said before, the spread, in this case the variance, increases with t. Okay. And there's another feature of Brownian motion that's very important and will be important for our case. If we think of time going along here, and we have 2 time points, t0 and t1, and we have our Brownian motion, then we can ask ourselves, what about the gap between Brownian motion at time t1, the later time, and Brownian motion at time t0, the earlier time? Well, that's a random variable. That depends on the sample path, and that can be shown to be normally distributed with mean 0 and variance, the time difference. So the time difference here is t1 minus t0, the gap between those points. Another feature of Brownian motion is that at time 0, Brownian motion starts at 0. So all these curves that I'm plotting here are starting at 0 and then moving out and spreading out from 0. We'll use these features that I've written down later on. Okay, now, as it stands, Brownian motion could not be used as a model for share price. And that's because Brownian motion is centered around 0. So shares are not centered around 0. The price of share is possible. So in order to overcome that problem of Brownian motion as a mathematical model for share prices, we introduce a concept that is Brownian motion with drift. So I just go back to my code and I run it in the hope that we will see Brownian motion with drift. And indeed, there's an example of a Brownian motion with drift. And what's happening is we still have a wiggle, but this time there's an underlying increase in the process. And the way Brownian motion with drift is defined is as follows. We think about a straight line. So if you like, this is what I'm plotting on the y-axis there. And we have a straight line, and the equation of this line will be y equals mu t. And in that case, mu would be positive. And then we impose around that line a wiggle. And that wiggle is our Brownian motion. In fact, we allow the wiggle to have as much variation as we wish. So that means that the Brownian motion with drift model is a straight line plus Brownian motion, but that can be multiplied by a constant sigma so that we can make it spread out as we wish. So sigma contains, well, let's put it this way. The larger sigma, the greater the wiggle. Now, obviously in this case, mu is greater than 0, but doesn't stop us from taking a negative value. And my next line of code there shows Brownian motion with a negative drift. And so we can see we've got a wiggle that's going down. Okay, now we've generalized our original Brownian motion model to the Brownian motion with drift model. But that's not actually good enough for our purposes, because as we can see from this figure here, the value that Brownian motion with drift takes can be negative. And no share price is negative. So we need somehow some way of making this positive. So I'll move on to the next slide. And I'll just remind us that the mathematical function exp is itself always positive for real x. So if we take our Brownian motion with drift, which is an example I'm showing in the figure here, and I take the exp of that, well, that is guaranteed to be positive because the exp of anything is positive. You might like to work out for yourselves, just to show for yourself, that when t equals 0, then this quantity here is 0, which makes exp of the quantity 1, because exp of 0 is 1. So this model here, the exp of Brownian motion with drift, starts from 0. So therefore, it's multiplied by a constant x0 to allow it to start from any value. So this process here has initial value, x0. So it's a more flexible model that can start from any value. And that we usually denote as xt. So the model xt, which is initial value multiplied by the exp of Brownian motion with drift, that is a straight line with a wiggle, that is referred to as geometric Brownian motion. And that is the basic model for share price. So let's see an example of that. So here is an example of Brownian motion, of geometric Brownian motion. And this is now a process that here we've chosen to start from 10. So x0 there is 10. And it wiggles around, and in this case, it's going down with time. But as I said, it's always positive. So there it takes values more or less greater than 2. It's always guaranteed to be positive. And if we look at another one, then we have another geometric Brownian motion that starts from the value 2, which I'll now show. There's the value 2, so it starts with the value of 2, x0 is 2, and then it wiggles around, and in this case, it is an increasing process. So we have there a very flexible model for share price that incorporates this notion of wiggliness, that is always positive, that can go up or it can go down, and that has a control in it, the sigma, for the amount of wiggle that there is. Okay, so this is our geometric Brownian motion model. Now, let's go back and look at our real data. So here we have real data that we saw before, the Marks and Spencer's share price. And what we're going to do now is we're going to try and think about how we can estimate the parameters mu and sigma of our model from these data. So which value of mu and sigma correspond to these data from the Marks and Spencer's share price? Okay, to do that, we need some more mathematics. So I'm going to write down the model again, xt equals x naught exp mu t plus sigma bt. And I'm going to take the log of both sides. So if I take the log of xt, well, I can, and that's a natural log, log to the base e, I can apply the log to both sides of the equation. And then the log of a product is the sum of logs. That's why log is a really nice operator. It turns multiplication into addition. So I end up with this. So I'm just splitting up the bracket into its two terms. And log and exp are inverse functions, so they effectively cancel each other out. So the log of xt is the log of x naught plus ut plus sigma bt. Now I'm going to record that there properly. The log of xt is this function. So it's a function of the initial value logged, and it's a function of the drift term, and it's a function of the Brownian motion term. Now I can think about what that would be at the previous time, t-1, the previous day for the share. Well, the first term there doesn't depend on t, so that stays the same. Then we have mu into t-1, and then we have sigma into b t-1. Okay, now I can subtract both of these. So I end up with log of xt minus log of xt minus 1. Now, when I subtract log x from log x, I get 0. When I subtract mu of t from, when I take mu of t and subtract from it mu of t minus 1, I just get mu. That's because t minus 1 is equal to 1. And then I get sigma into bt minus 1. So therefore, I have that the log of xt minus the log of xt minus 1 is equal to mu plus sigma bt minus 1. So this on the left-hand side there is random. And what I have on the right-hand side there is auto-random. Now, when we're dealing with random quantities, we often try to understand them by taking their mean and finding their variance. So I'm going to find the mean or expected value of the left-hand side. And that's, of course, going to be the mean of mu plus sigma bt minus 1. And the only random part is here. And by the rules of the expectation, we can take the expectation in, it's a linear operator, and apply it to that random part. So we get mu plus sigma, the expected value of bt minus 1. Now, let's just think about what we know about bt minus 1. Well, we saw earlier that bt minus 1 is normally distributed with mean 0 and variance the gap between these two times. Well, the gap between these two times is 1, so that's normally distributed with mean 0 and variance 1. So if I go back here, I just get the expected value of log xt minus 1 is mu plus sigma times that expected value, which is 0. So I just get mu. So the expected value of this quantity here is just mu. So let's move on to the next slide. So we have our expression for log xt minus log xt minus 1. And that expression is mu plus sigma beta t minus 1, exactly as we saw before. We've found the expected value of the left-hand side to be mu, and now we're going to work out the variance. So the variance of log xt minus log xt minus 1 is equal to the variance of mu plus sigma beta t minus 1. And the only thing that is random is this quantity. So by the properties of the variance, we don't worry about a constant. The constant added on doesn't change it, doesn't change how the random variable is spread out. The sigma is pulled out and squared. So we get sigma times the variance of bt minus 1. We've already stated that this is 1. So the variance of that quantity is sigma squared. Okay, so what we've actually established now is that the expected value under our model of log xt, the log of the share price at time t, minus the log of the share price at time t minus 1, is equal to mu, and the variance of that quantity is equal to sigma squared. And therefore, and this is a standard feature of statistical estimation, if we want to estimate the mean, we would take the sample mean. So if we want to do estimation, which we want to do in this case, to estimate the mean mu, we take the sample mean. We take the sample mean of the observed quantities. So they would be log x2 minus log x1, log x3 minus log x2, log x4 minus log x3, yes, and so on. So we can estimate the value of mu corresponding to the geometric of Brownian motion that models this time series here by the sample mean of those quantities there, the differences of the logs. Similarly, we can estimate the sigma squared by taking the sample variance of those quantities. So we can estimate both of the parameters of our model. Okay, so we've shown by the above argument that the expected value of log xt minus log xt minus 1 is equal to mu, and the variance of that quantity is equal to sigma squared. And in fact, it's not hard to demonstrate that log xt minus log xt minus 1 is in fact normally distributed with mean mu and variance sigma squared. So let's see whether that applies in action. So what I'm going to do now is I'm going to plot on my first graph coming up the values of log xt minus log xt minus 1, this quantity here. I'm plotting these against time. So I've taken my original Marks and Spencer's time series, I've taken the logs, I've taken the differences at every time point, and these are the values that result. Okay, so it could be, it's not without the realms of possibility that these values here are coming from a normal distribution. I could look at the histogram of those values there, and there's the histogram, and again, that could be coming from a normal distribution. So it seems that this model that's based on geometric Brownian motion and that leads to that result there, it seems that this model could well apply to the Marks and Spencer share case. Okay, now if we do our estimation procedure by estimating mu as the sample mean of the data that we have, so log x2 minus log x1, log x3 minus log x2, and so on, then we find for the Marks and Spencer data that mu is 0.0004. Similarly, we find that sigma squared, the estimate of the variance, which is the sample variance of all the differences of the logs, is 0.0004. So if I plug those values into my original geometric Brownian motion model, estimating sigma hat by the square root of sigma squared hat, if I plug those in, let's see what sort of curves result. So I need to run this code here. And at the top there, we have the original data. So that's the original share price data that we've seen several times. What I have at the bottom there is a simulation from geometric Brownian motion. From this model here, that is the geometric Brownian motion model with the parameters there, mu and sigma, estimated from the data from Marks and Spencer. And what we can see is that this first simulation, this first sample path from geometric Brownian motion looks quite similar to the Marks and Spencer data. And that's really very encouraging. It's saying that, effectively saying that we have a useful and sensible model for the share price data. Now, obviously, every time I run the code, I will get a different realization. So here's a different one, which perhaps looks slightly different from the data themselves. Let me do it once more. So there's a third sample path from geometric Brownian motion. And again, it looks quite similar. Not exactly the same, of course, because it's a random process, but it looks quite similar to the Marks and Spencer share data. So what we've developed today is a model, a mathematical model that can account for, that can explain share price movement. And this is really something quite exciting because share price movement is hard to explain, partly because it has potentially a structure to it, like a downward structure, and also because it's a random process. It's going up and down each day. it's a wiggling process. And we've managed to model that using Brownian motion, which is our basic model for a wiggle. We extended Brownian motion to Brownian motion with drift so that we could take account going down or going up. And then we remarked that Brownian motion with drift could take negative values. That wouldn't be appropriate for a share price. And then we used the EXP of Brownian motion with drift to form another process called geometric Brownian motion, which is the standard model for share price behavior. Now, of course, it's not a perfect model. And just like we saw with the first graph, where we had the effect of the COVID pandemic, sometimes the model doesn't work particularly well. So people have worked on modifications of this model, and that's a current research topic. But the geometric Brownian motion model is an excellent model in general for share price behavior. So I'm going to finish this presentation with a little more mathematics. And what I'm going to do is I'm going to think about the interpretation of log xt minus log xt minus 1. So that was a quantity that came up before, and it was a quantity that we used to estimate the parameters of geometric Brownian motion. Okay, does this quantity have a financial interpretation? Well, in fact, it turns out that it does. I can do a little bit of mathematics on this. So I can write that as the log of xt over xt minus 1. That's because the log of a ratio is the difference of the logs. And that's an important and useful feature of the logarithmic function. I can write this now as the log of 1 plus xt over xt minus 1 minus 1. So just to state what this xt over xt, that, if you like, is the share price today. If today is t, divided by the share price yesterday. Now let's go back to this log. What I've done there is I've written this as 1 plus the original thing minus 1. And why can I do that? Well, that's straightforward. If you have 1 plus anything minus 1, I get back to anything. And that's, as I said, straightforward. But why would I want to do that? Well, because I know that there are expansions for quantities such as log of 1 plus x. And the expansion of log 1 plus x is x minus x squared over 2 plus x cubed over 3, and so on, plus and minus and plus, and so on. And that's an expansion that is valid for x between minus 1 and 1. You might like to actually obtain that expansion for log 1 plus x for yourselves. You can do it using a Taylor expansion. Fx is f of 0 plus the first derivative of 0 multiplied by x plus the second derivative of 0 at 0 multiplied by x squared divided by 2, and so on. So you might like to apply this Taylor expansion to the function log 1 plus x fx and see what you get. So the upshot of that is that I can approximate log 1 plus something as just the something itself. I can cut off the Taylor series here to get an approximation, and I can approximate this as xt over xt minus 1 minus 1. And that equals xt minus xt minus 1 over xt minus 1. And that quantity is referred to as a relative return. So that's a financial name. And why is that? Well, because on the if we think about time going along here, and say I buy a share at time t minus 1 at a price of xt minus 1, and then I sell it again at time t at a price of xt, then the return that I get for doing that is going to be what I get minus what I spent. So as I said, I'm buying here, I'm selling here. So that's my return. Could be negative, but that is my return. And if I want to know what that return is relative to my original investment, I get my relative return, which is xt minus 1, all divided by my original investment, xt minus 1. So the quantity that we've been working with that comes naturally out of geometric Brownian motion, and that is used for estimating the parameters of geometric Brownian motion, is approximately the relative return, which has an immediate financial interpretation. So just to conclude, we've met Brownian motion, we've looked at some of its properties, we've extended that to Brownian motion with drift, we've extended that to geometric Brownian motion, which we use as a model for share prices. We've seen how to estimate the parameters of that model, and this we've put into practice by seeing that it can be applied to model shares such as Marks and Spencer. We have also said that the model, like all mathematical models, has some drawbacks, but it really does provide a very good mathematical model for share price. And in fact, it's the model that is used for pricing financial products such as derivatives through the Black-Scholes-Merton equations. They are very famous equations. They led to the award of the Nobel Prize, and they help us to understand how to price complicated financial products. So if you're interested in this sort of material, if you're interested in finance, you can study these mathematical models and a lot more on the Mathematics with Finance degree at the University of Plymouth. And I hope you've enjoyed this short video, and you've seen something about these very nice stochastic models for random processes over time. Thank you very much.